In the first installment, DeepSeek v4 Flash on DeepInfra completed 7 of 9 file editing agent runs. The total build cost was about 0.6 cents, so the API looked practical. That result is the reference point for this episode. This is not a bonus benchmark attached to the API story. It is a standalone sequel with a different question. If we compress the same model family to just 1.75 bits per weight and move it onto a roughly 96 GB local GPU system, how much of that agent capability survives? The order matters. We first established 7 of 9 through the API. Now we can interpret the local result against something concrete. The local build used the unsloth GGUF release of DeepSeek v4 Flash, specifically UD-IQ1M llama.cpp reported IQ1M at 1.75 bits per weight. The model has about 284.3 billion parameters, and the complete GGUF was about 86.9 billion bytes. It ran across 3 RTX 3090 cards and 1 RTX 4090, each with roughly 24 GB of memory. After the model was loaded, an idle NVIDIA SME capture showed 84.01 of 95.988 GB in use, leaving 11.987 free. That is an absolute system-wide loaded state measurement. We did not capture a preload baseline, so it is not valid to call 84.01 GB model-only VRAM. The snapshot also cannot prove the exact tensor placement on each GPU. Both deployments faced the same fixed agent contract, 3 task types, repeated 3 times for 9 runs. They received the same short system prompt, task fixtures, tool schemas, visible tests, hidden tests, high reasoning setting, 12-turn limit, 3,000 token output cap per response, and repetition seeds. Every run started from a fresh fixture. The agent could read files, write only solution.py, and run the visible tests. A run counted as successful only if it returned a final answer, passed both visible and independently executed hidden tests, preserved protected files, and wrote nowhere outside the allowed implementation file. But the conditions were not identical in every respect. The API used provider-reported FP4 on DeepInfra. The local build used GGUF IQ1M through llama.cpp. Runtime, infrastructure, and quantization format all changed, so this comparison cannot isolate quantization as the sole cause of any difference. The API reference completed 7 of 9 runs. The 1.75-bit local deployment completed 6 of 9. That is substantial retained capability. The compressed model still used tools, edited code, and passed hidden tests in 2/3 of the sample. It also completed all 3 event rollup tasks. The misses were uneven. Inventory fell to 1 of 3, while dependency batches reached 2 of 3. In one failed inventory run, the model guessed test file names, then spent a full 3,000 output tokens reasoning after it finally received the real test failure without writing code. In another run, visible tests passed, but none input raised attribute error instead of the required value error. Importantly, that validation boundary mistake also appeared in the API condition. 9 runs are too few for a universal quality estimate. The careful conclusion is usable capability with measurable inconsistency, not a definitive score for IQ1M everywhere. The most revealing contrast is between token speed and task speed. Local median decode throughput was 40.33 tokens per second, with runs ranging from 39.03 to 42.69. For a model of this scale on this hardware, generation itself was not crawling. Yet median end-to-end time was 144.96 seconds, compared with 15.8 seconds for the API reference, a 9.17 times gap. The local model produced a median of 345 completion tokens per run. The API median was 984, so local output was 3.20 times longer. Median turns were 5 locally and 6 through the API. The The delay was not accompanied by more conversational round trips. It was observed alongside substantially longer completion output inside those turns, although this comparison does not isolate a single cause. Tokens per second measures the engine. Seconds to a correct artifact measures the agent. The local server used an 8,192 token context window. Across 45 model responses, the largest single request totaled 5,399 tokens. 0 responses reached the 8K context ceiling. 3 responses, however, ended at the 3,000 token output cap. This distinction changes the next experiment. Expanding context would not address a limit we actually observed. Shortening the reasoning budget might. At least one failure showed long reasoning, delaying the moment when the model needed to write code or call a tool. Still, 3 capped responses do not prove that every failure came from the cap. The evidence says the output boundary bound 3 times. It does not reduce all error modes to one cause. The local runs had 0 API billing, but that does not mean 0 cost. The hardware, electricity, setup time, and maintenance still exist. And because the API reference cost only about $6 for all 9 runs, this experiment does not support a simple payback argument. The stronger value of local execution is control. We can change the context, output budget, reasoning policy, runtime, and placement without waiting for a provider. The best next control is not a larger context window. It is the same model and fixtures with a 1,500 to 2,000 token response cap, or a non-thinking mode to test whether earlier tool use improves completion. That would be a new inference policy experiment, not a retroactive correction to this result. So what survived at 1.75 bits per wait? 6 successful agent runs out of 9, including a perfect 3 of 3 on event rollup. The system decoded at 4033 tokens per second, but took a median 100.96 seconds to finish a run. Its loaded state system-wide GPU usage was 84.01 of 95.988 GB. No response hit the 8K context limit, while 3 hit the output limit. We should not call this equal to the API, and we should not say quantization alone removed one success. We changed a bundle of conditions. What we can say is that aggressive compression preserved a surprising amount of practical agent behavior, while exposing a new operational problem, knowing when to stop reasoning and act. The benchmark that matters is not only how quickly tokens appear, it is whether those tokens become working code before the budget runs out.